now recording. Let's get the slideshow set up. Okay. Before we get there, last announcement. The student course evaluations are open, available. Have y'all done those before? You have. Okay. What's that? Yeah. Well, that's for courses that are hard that you need the points, you know. This is such an easy course, you don't need it.
It's so easy.
Yeah, it's so easy. All right. So please do those as soon as you can. Please do all that you're requested to do. I've asked students before. Have you done them for this term already? How long did it take? 5 minutes. Okay. Might take you a little longer, but 5 to 10, 15. That's all. I've always hear an answer somewhere in that range. So it isn't an onerous thing. So please get it done. Okay. Now, if you want to wait till a little later in the term, you certainly can. If you want to see what that last test looks like and the final looks like, you can do that. But just don't put it on the back burner, and then when you finish your finals, I'm out of here, and forget completely about it. So please do the student course evaluations, not forgetting them. All right. Any questions on anything we've covered so far? All right. We are on example 6, page 173. About the middle of the page there, rational function, and they tell you it's got, they shouldn't tell you that. Okay, so let's sketch the graph of this function. F of x is equal to x squared minus 9 divided by x squared plus x minus 2. No. Okay, I read that from the line above. Okay, x squared minus 2x. Sorry about that. I was saying that is not what they said it was going to be. Okay. All right. Now let's see if we can get that corrected. X squared minus 2x minus 3. All right. What's the first thing you want to do to sketch the graph of this function, not the one above, but that one? A little louder.
See if there's a vertical asymptote.
Okay.
See if there's a vertical asymptote.
Okay, how do you determine that?
Look at the ratio of the first times. No,
What?
the ratio of the first time.
That's horizontal asymptote.
Okay.
Yeah. Okay, and you can do that if you want to. Since you're there, you can do it. But actually, a little time out here. When you started off saying vertical asymptote, I was all in favor, because what you're going to do, how do you do vertical asymptotes?
You look at the denominator.
And where it's not equal 0. So what do you got to do on that one to determine that? Factor. Okay. Good first step on all these rational expressions. Let's just go on and say it. Factor everything in sight. Factor numerator, factor denominator, then start your procedure. Okay? You may come back to this form, but you got it here to look at, like ratio of leading terms. Yeah, it's more convenient before you factor, but we're not going to do away with it, so let's factor that. Does that numerator factor? Second? X. X times x. A little louder. Minus 3 plus 3. Perfect. Okay. Good. That's the numerator. How about the denominator? Will that factor? Well, I'm not really sure, but let's try it. Where would you start? X times x again. You got that one down. Okay, good. Next. Different signs, so plus and minus, or minus plus, it doesn't matter. Plus 1 minus 3. Okay? Now, why is that? Well, the only possible factorization of 3 is 1 and 3. Okay? But you better have the larger number with the negative sign, because the negative wins here. And let's check it and can see x times x is x squared, minus 3x plus x is minus 2x minus 3. Yes, that works. Now what do you notice?
And get rid of, there's, I don't know what's called, the x minus 3.
Okay, is a common factor between numerator and denominator, so we can divide it out. However, what we just said was that denominator can't be 0, so that means x cannot be what? The denominator can't be 0.
X cannot be
-1, but neither can it be, second, +3. Okay. Now, the +3, you almost want to forget because you got rid of it. But you see, the original problem still can't have a +3 in that denominator because that's going to make it 0. That'd be 9 minus 6 minus 3, that's 0. So you cannot have a -3 there. I mean, a +3 there. So you have two different situations here. This one is going to be a what? That right there is your vertical asymptote. But the 3 is not a vertical asymptote. Okay? Because it canceled out. Okay? What's it going to produce? A hole in the graph. So you got to remember that. This is your vertical asymptote. Go on and identify it now. This is your HOG, your hog, the hole in the graph. Okay, never mind. Okay, I just made that up. Okay, so that's not H composed with G either. So never mind. Okay, that's going to be your hole in the graph. Now, what else do you notice? What do you want to do next? I'll let you decide. Horizontal asymptote, and how do you get that? Okay, and actually you can do it either with the original problem or with what's left of the original problem after you factor. And what's the ratio of both of those leading terms? 1. Okay, your horizontal asymptote then is going to be, it's not just a number, something's equal to 1. What is it? Y. That's the y is equal to 1. You can look at that and see f of x is y. Y is equal to 1. For very large x's, that's what that's going to be. So there's your horizontal asymptote. So we've got vertical asymptote, horizontal asymptote. You got your hole in the graph, okay? Anything else? X and y intercepts. Which one you want to go for first? X-intercept? Okay, how do you determine the x-intercept? I thought you said you wanted to do that one. What's x-intercept?
I'm just trying to remember how to do it again. Set the, that's not the one where we set y equals 0.
Why not? Okay. Think of this. Okay. X-intercept is where it crosses the x-axis, right? That's where it intercepts the axis, right? What's true about every point on the x-axis? Y is equal to 0. So yeah, that's how you find them. The jar ends here. If I can get my pen to work. Increase the class size by 25% or 33%. Good. Okay. So x-intercept is where y is equal to 0. Okay? So what's your y? F of x. And when would that be 0? No, that's where your vertical asymptote, that's where the denominator can't be 0. We want where y is equal to 0. The denominator doesn't
Just set the whole problem equal to 0.
Okay, except, okay, it's a rational form, right? Okay, so let's say you have a rational number. Give me a variable for it. We don't have to use x, y, or f or something. Just give me another variable. Second?
T.
T, okay. And T is some rational expression. We'll call it an N over a D. I don't know where I came up with those letters. Now, if T is equal to 0, what has to be true about either N or D? Anything? The D, N, what should you say? Yeah, if T is going to be 0, that's what we're trying to do, get the y equals 0. For this to be 0, what has to be true about either N or D? What fractional form is equal to 0? What 0? N or D? The D, if D is 0, it's undefined. It's a numerator. Doesn't matter what D is as long as it's not 0. We've already taken care of that. It's the numerator. If you have 0 over 4 million, guess what you got? 0. 0 over negative 3. 0. It is 0 over anything. So all that matters is what this is. If this is 0, that makes that 0. So therefore, what are we concerned with here? Yes, the numerator. Now we've already eliminated that one, so don't go back to that. But what about this one? It's a horizontal asymptote if the yes is equal to what? X plus 3 is equal to 0. X equal negative 3. Subtract 3 from both sides. Okay. Okay. You said that the numerator has to be 0, right? So x plus 3 has to be 0. So x plus 3 is equal to 0. Subtract 3 from both sides.
The first problem.
Oh, up there?
Yeah.
Okay. Yeah.
No.
All right
Yeah,
here.
I was looking there. I was gonna put 3 in for the x. So 3
Right.
plus 3 is 9. 9 minus 9 is 0.
Okay. But the thing is, we already took care of the 3 here.
Okay.
Yeah. That's why I said we've already dealt with the x minus 3. Don't go there. We're looking at x equals negative 3. But an x-intercept is not an x value. It's an ordered pair. What is an ordered pair? I can tell you the x value. Say again? Negative 3, not 1. What do we do to do it? Get it? Set y equals 0, so it's negative 3, 0. All right. Now, what's the last remaining clue that we need to discover? Y-intercept, okay? Now, what defines the y-intercept? Diamonds here. Find you, but then I'll lose you. There you go. Good deal. Oh, good, thanks. Didn't say this earlier, I probably should have. I do need those quizzes in because the odds are the test is going to be Tuesday. So please get them in now. You can at least see what you missed if you missed anything on it before the test. So how do we determine the y-intercept? Say x equals 0. And that's a pretty easy thing to do, isn't it? You can either do it in the first problem. If x equals 0, all these disappear, and what do you have? Which is? Positive 3. Or if you come over here and set these two equal to 0, you get 3 over 1, that's 3. So whichever way. So how do you write? But you see, I need that as an ordered pair. How do I do that? 0, 3. You got it. All right. We've got most of what we need to graph our function. Okay. At least to get started on the graph. Okay. Boy, this is pretty nasty. Okay. What I'm going to do is put these pieces of information separate them, get them out of the way, the crucial pieces, and they are these. Okay. Vertical asymptote is x is not equal to -1. Okay. And then I'll do this. I just made up this terminology. The hole in the graph, the hog, is x can't be equal to 3. Okay. We got that with these two terms canceled out. X can't be 3 because it would make a 0 in the denominator, but it's going to disappear, so it's not a vertical asymptote. All right, horizontal asymptote, what's the next thing we did? And that was y is equal to 1. X-intercept, that was -3, 0, and y-intercept was 0, 3. All right, now I can erase everything else. Okay, let's not erase all the ink, but let's erase this. Do we need to keep the actual function? Maybe it's good to, I don't know. Just so we remember what we're doing. Okay, I think we can go and erase this part too. See, you'll have graph paper, so you can do your scratch on one sheet and graphing on the other sheet, and everything will be hunky-dory. I don't have that privilege here. Let's see. Let me put my horizontal axis here. Tick off 1, 2, 3, 4, 5, 6, 7, 8, -1, 2, 3, 4, 5, 6, 7, +1, 2, 3, 5, 6, 7, -1, 2, 3, 4. Okay. Not very well spaced, but we can live with it. How do I indicate vertical asymptote x not equal to -1? Okay, go left 1, x equal -1, do a vertical line, dotted vertical line. I like to do it in red, meaning you can't go there. Don't touch it. Don't get close to it. It's hot. Okay. So we got that one. Horizontal asymptote. How would I do that? Up 1. Okay. Just don't say yours. Okay. And there will be your horizontal asymptote. Okay. Now that basically defines your new coordinates, you might think. Okay. Everything's going to be in one of those quadrants. Okay. So let's go next to our x-intercept. And what does it happen to be? So we go left 3 and don't go up or down. And for some reason, my pen is not writing. So right, no. I want black. Okay, now -3, 0. There's your x-intercept. I think I know beyond the shadow of a doubt where this function is going over here. Okay. Now, how about your y-intercept? What's it? Say again? Up 3. Okay. 1, 2, 3, right there. I think I know where that one's going. There's just one more thing I haven't plotted, and what's that? My hole in the graph. That's at x equal 3. You can't have anything at x equal 3. So I'm going to draw the graph, but then come back and put the hole in the graph. I know where this is going. As x gets larger, it has approached the horizontal asymptote. That's your end behavior. As it decreases from here, it can't cross the vertical asymptote, so it has to be approaching it. So that's how that one looks. Same thing over here. As it's going to the left, it can only approach the the vertical asymptote. It can't touch it. And over here, this is where it's going in the long run here. Except for x equals 3. There's your hole in the graph. Does that make sense? Okay. Let's see. Well, they don't do it. Look at the book and see how they did it. They picked some more points. Good for them. They just like plotting points. You knew it had to be over there in the lower left, and it had to be in the upper right, except for the hole over x equals 3. Okay. By the way, Diamond, by the way, we probably will have the test on this chapter on Tuesday. Okay. All right. All right. Was it something I said? No, I'm just kidding. Okay. That's how the graph looks. Their picture is almost as pretty as ours, but not quite. There is a checkpoint there. I'd say well worth your effort to do that. Now, there is a subsection here on slant asymptotes. Okay? Frankly, I don't find these all that useful, but they are there. Here's the deal with that. Okay? I'll just basically introduce it. You're not going to be tested on it. Okay? Let's see if they have a slide on it. This is all from the previous one. These are additional points. Okay. Yes. Okay. Slant asymptotes. Okay. Basically, if you have a situation that your f of x is 1 degree, the numerator is 1 degree larger than the denominator, then either do synthetic division like you could do with this one, or long division if this is x cubed and x squared. You can't do synthetic, then do long division. Do division of that, and you'll come out with an equation for y, because this will go into that x times. So y is equal to x plus or minus something is going to be a line. That becomes your slant asymptote. Okay? You still have a vertical asymptote at x. Where's your vertical asymptote? Vertical asymptote. -1. X can't be -1. So there is your vertical asymptote. When you divided that, you got, they showed it, x minus 2. You'll have a remainder. Who cares about the remainder? Here, all you're interested in is that quotient. Y is equal to x minus 2. You plot that just like you would anything else. Intercept at -2, slope of +1. There you got it. Okay? Now your graph is going to be inside those things. Here is what you do next, is find either the x or the y. It's not going to have a horizontal asymptote because it's a slant. The horizontal is now slanted. Okay? So it's not horizontal anymore. Okay? So don't even bother looking for a horizontal asymptote. Ratio of leading terms is x. As x is large, that goes to infinity. Positive infinity here, negative infinity there. Sure enough, that's where it's going. Positive infinity, negative infinity. Okay. So there is no horizontal asymptote, there is a slant asymptote. Your intercepts then, I like to do the y-intercept first because it's so easy. Just set x equals 0. What does that give you? Say it. Okay. When x equals 0. Okay. Okay. When x equals 0. The whole thing. 0. So that's not only your x-intercept, it's your y-intercept. So you have this point here. So that means you're in between your vertical asymptote and your horizontal asymptote. There you are. You have to be like that. And it's a good guess that the other part's going to be down here. But what you would do is pick a value like -2, plug it in, and see where you are, and you'll find out you're down there. Okay? So that's how you do this. Don't worry about it. We're not going to do these. These are also sometimes called oblique asymptotes. Okay? It only works if the degree of the numerator is 1 more than the degree of the denominator. If this is x cubed over x, don't even bother. It doesn't have any kind of horizontal or slant asymptote or oblique asymptote. It's just going away. Okay. So don't sweat those. So as it says here, the first thing you do is your division. Now they say long division. This one you could have done it with synthetic division because your divisor coefficient of 1, exponent of 1. So you could have done that. And you don't worry about the remainder. All you are concerned with is this. Y is equal to x minus 2. Graph that, dot that line in, that's your oblique or slant asymptote. Okay? All right. Oh, and what they say here, one reason we forget this about, I said, forget about the remainder. The reason that's legal to do, what you're looking for here is end behavior. And if x is very, very large, this is going to 0. I mean, this is going to a huge number, that's saying 2. 2 over 4 million is awfully close to 0, okay? So that's going to 0. 2 over negative 4 million is still awfully close to 0. So this doesn't enter the picture anymore. And you see, as you get further and further on, you're getting closer and closer to that line. In here, yeah, it's nowhere close to the line, okay? In fact, here it's way, way, way far away. But you see, we're not worried about that. The horizontal asymptote and the slant asymptote, the vertical asymptote, oblique asymptotes, that's for end behavior. What's happening in the long run is getting close to that slanted line, okay? So, we're not going to bother this. What would be your first step? Say again? Factor? Actually, not a bad idea, but it's not going to help you. But yeah, what did you say? Divide it. And how would you divide that? Use synthetic. I would agree. And what would you be on the outside of the synthetic? Plus 1. It's whatever that number is, the opposite sign. Okay. All right. And you go on. They did factor, and that helps you find the x-intercepts. Okay. Doesn't help you find the oblique, slant asymptote, but it does help you find the x-intercepts because where that numerator is 0, that's where your horizontal asymptotes are. X equals 2 and x equals negative 1. Okay? Those are going to be very helpful because the next thing we're going to do is, they say long division, synthetic division will work. That gives you x. F of x equals x. That's going to be the identity function right through the origin. Okay? Slope of 1. Okay? Don't worry about the remainder. That's not going to help you at all. Okay? So there's your slant asymptote. So your y-intercept, that was pretty easy to do. Just say x equals 0, and what do you get? 2. Exactly. So your y-intercept is 0, 2. X-intercepts are 2, 0, and negative 1, 0, right? So we got basically, there's the x-intercepts. Vertical asymptote, we knew that because that denominator, x can't equal 1. So that's your vertical asymptote. Okay? I should have said that earlier. And your oblique or slant asymptote was the line y is equal to x. So plot off, and then they do additional points. You really don't need them. Let's do this. Let's do the ones we knew about. Vertical asymptote, x not equal to 1. The oblique or slant asymptote, y is equal to x. And then one point was 2, 0, negative 1, 0, and 0, 2. Who needs another 2 points there? You don't. It just approaches from here, the slant asymptote going this way, the vertical asymptote going this way. From this point here, it approaches the slant asymptote going that way, vertical asymptote going that way. You don't need those other points unless you just want to make it prettier, which I'm really interested in. So we can live with it, right? All right, but you're not responsible for that. Now, applications, I have done these occasionally in the past, but it says there are many examples of asymptotic behavior in real life, and this is example 8, shows a vertical asymptote can help you analyze the cost of removing pollutants from smokestack emissions. Okay, and here's basically what we got. A utility company burns coal to generate electricity. That's pretty common, okay? I would say most of our electricity is probably generated using coal. More and more it's going to natural gas, much cleaner. A little bit is done nuclear, very clean in producing the electricity, but what you do with the waste afterwards, not so clean. And a little bit is done by hydroelectric, especially here in the southeast. Yeah. What's that?
I live right beside Block 17.
Okay.
So the dam, that's what.
And which river is that on?
Warrior.
Warrior. Okay. And is that a hydroelectric plant? Yeah.
Well, it is. They're working on it right now. It's shut down.
Oh.
But that's what it is.
Yeah. But that's the cleanest. But the trouble is, we've already built all the dams we can build in the easy to build places, and most people aren't going to give up the land from now on. So, not going to build many more. Okay. So, but this is coal production. Electricity produced by burning coal, and the cost in dollars of removing a certain percentage of the smokestack pollutants is given by this. Now, of course, that percentage is going to be between 0 and 100. You're never going to remove it all, okay? You're a member of the state legislature considering a law that would require utility companies to remove 90% of the pollutants. The current law requires 85% removal. How much additional cost would the utility company incur as a result of the new law? Well, you know, you don't need any of the other stuff here. All you have to do is plug in a 90 here and a 90 there. That'll give you the cost, the new cost, and 85 here, 85 there. That'll give you the old cost, and see what the difference is. And surprisingly, I think you'll find it's a lot more expensive to move that last 5% than it was earlier. Okay, but so you don't really need any of the things we've been doing to do that. But it's still sort of fun to look at the graph because the current law requires that. That's what I said. Evaluate that. $453,333 to remove 85%. Remove 95%. Look at that. Up to $720,000. Okay, so significant cost increase to just get 5% more out of there. But if that's causing people with asthma and babies and other things to have difficulty breathing, you might want to do it. Okay, what's the public health cost if you don't do it, as opposed to the cost of doing it? Okay, now, so the new law. So you see, there's absolutely nothing in this problem. It just was a rational expression. You didn't need a graph at all. So that was a pretty simple thing, but you could draw the graph and see that. Okay. Any questions? There's another one on finding minimum area. And frankly, not much. We'll just leave those. Let's do the vocabulary. Functions of the form f of x equal n of x over d of x, where n of x and d of x are polynomial functions, and d of x is not the zero polynomial, are called blank blank. Look at the title just above it. 2.6. Rational functions, okay? Number 2, when f of x approaches either plus or minus infinity, as x approaches some value a from the left or from the right, x equal a is a blank blank of the graph of f. X equal A. X is going, f of X is either going positive infinity or negative infinity. Vertical asymptote, perfect. When f of X approaches B, as X approaches X approaches first plus or minus infinity, then Y equal B is a blank blank of the graph of F. Horizontal asymptote, very good. And number 4, for the rational function f of X equal n of X over d of X, if the degree of n of X is exactly one more than the degree of d of X, then the graph of F has a blank or oblique blank. Second, slant asymptote or oblique asymptote. Okay, homework exercises, either 5 or 7 or both. Any of the odds 9 through 15. Any of the odds 17 through 39. And if I were you, I would do all 4 of 41 to 44. However, only 41 and 43 have answers in the back. Do either 45 or 47 or both. And then you don't need to do 49 in those groups unless you just want to. Okay? The 63 through 66, they say it requires a graphing utility. So if you got one, you can play with them. You don't have to. Graphical reasoning, again, I would suggest maybe playing around with those. You should be able to determine some things just looking at them. 71 is very close to that one we just looked at, but you're not responsible for it, so I'll let you decide whether you want to do that. Page design was the other one that we didn't do, so you don't need to worry about that. 75 you can do. It's not a slant asymptote or anything else, but you may be interested in doing that. There's some true false, 77 to 79. Probably not a bad idea to read through those. I think those answers are in the back, 77 and 79. There's some multiple choice there that might be sort of fun to look at. You should be able to figure those out too. And that's, yeah. Don't see if there was a potential paper topic. There does say there's an extended application analyzing the total number of military personnel on active duty from 80 to 2010. If you're interested in doing that and want to build a paper around it, which I wouldn't be interested, but if you are, go for it. We're not going to do 2.7, so don't sweat that. It's good stuff, but we just don't have time to cover it. So don't worry about section 2.7 and its exercises. But there is a chapter summary. Breaks it down by section, so you're only concerned with 2.1, 2.2, 2.3, 2.4, 2.5, and 2.6. However, 2.6, the part on slant or oblique asymptotes, you can sort of ignore that. Don't worry about 2.7. The review exercises, again, they breaking it down by sections, so you could do number 1 if you're interested, any of the odds 3 to 7 if you're interested, number 9, 11, that's 2.2, 13 or 15, 17 or 19, and 21 if you want to do some more practice. 23 is a good one to do, and 2.3, 25, and 27, and 2.4, 29, either 31 or 33 or both, and 37 or, 35 or 37. Now, we didn't do those with complex numbers. So, in fact, 2.4, a lot of that you can leave off. In fact, I'd say all those. Don't sweat it. I don't think we're going to have any with that. But you may want to take a look at it if you're interested in pursuing that. 2.5, 39, 41, 43, or 45. There's Descartes' rule of signs. We did that before, but remember that's a potential paper topic. Either who is Descartes, or how did he develop his rule of signs, or how do you use it? 2.6, 47, any of the odds 49 to 55. I don't think you need to do 57. Okay, so anyway, more exercises if you're interested. By the way, even these review exercises, countcheck.com, tutorial help and worked out solutions for the odd number exercises. Now the chapter test, that would be another good thing to look at, and the advantage of this one is in the back of the book, your chapter test, I think all the answers are there. Still at countcheck.com, it's only the odd number, but all the answers are there. So you can do any that you want to, 1 through 9, 1 through 8, no, 1 through 7, okay. 12, 13, 14, 15, 16, and you can stop there. So any of those would be additional ones if you just need them. There's a thing about proof in mathematics, so about the remainder theorem, the factor theorem, linear factorization theorem, and the fundamental theorem of algebra is mentioned, but they don't do it. But when that mention of fundamental theorem of algebra, if you take a look at that, you'll see a few other potential paper topics, like Abu al-Khwarizmi, or something like that, okay? He was one of the earliest mathematicians actually to develop algebra, okay, or to do a lot with it. In fact, the word algebra comes from an Arab name, algebra, okay? The guy who first did it. It's not this one, but someone similar to him. Okay, you'll notice there fundamental theorem of algebra. Gottfried von Leibniz is mentioned. Jean d'Alembert is mentioned. Leonard Euler is mentioned. Joseph Louis Lagrange is mentioned. Pierre Simon Laplace is mentioned. And Carl Friedrich Gauss is mentioned. So lots of different people, lots of different topics you could choose from there. And then finally, factors of a polynomial. There's a proof for that too. There's a little thing on problem solving. PS, problem solving. And that's it. Let's move now to chapter 3. I don't have a lot of time for chapter 3, but let's get as much covered as we can in chapter 3. We've got basically, 25 minutes? So let's go to chapter 3. We will have the test on chapter 2 on Tuesday, and then Thursday is the last day of class. I'll be returning all your quizzes and tests to you on Thursday. That means you better get in that quiz. If I haven't gotten a quiz by Thursday, that's going to be a 0. Not a good thing to have on a quiz. Also, Thursday, last day of class, is the last day to turn in your papers. Get busy this weekend. Here you have a test and a paper. I told you to get those papers done early, didn't I? Okay, so get those done. This last test, the one we have on Tuesday, it'd be great if you could finish the test Tuesday, Wednesday, or sometime Thursday, so that I can get it back to you so you'll have it to study for on the final. So this one you don't need.
When's our final? Will it be the next Tuesday after that?
It's the next Tuesday, the following Tuesday. Yeah. So we'll go there. So let me go back here one more, and we'll go to chapter 3, exponential and logarithmic functions.
If we don't finish our test on Tuesday, will we have time in class Thursday to do it?
Not in class, during office hours. Tuesday, Wednesday,
You
or
said you were
Thursday.
handing it back, so I didn't think we were going in for any more lessons.
What's that?
You said you were handing back all our stuff Thursday?
Yeah.
So I didn't think we were going to do more stuff.
Oh yeah, we're going to continue in chapter 3. Yeah. This is, you see in the final exam, we'll have probably 4 questions on chapter 1, 4 questions on chapter 2 and 2 questions on chapter 3. So I want to cover enough so you have at least a little bit of chapter 3 there. Okay. All right. Get the slideshow set up from current slide. Okay, what we're talking about in chapter 3 are 2 more types of functions. To do a little bit of mental review here. Chapter 1, we did the parent functions. You did the, go back and look at those power functions, the linear functions, the quadratic functions, the cubic functions, the quartic functions, the absolute value function, the reciprocal functions. You did those kinds, just general parent functions. Chapter 2, we specialized on polynomial functions, and then the last section on rational functions. This one we're covering 2 more types of functions, exponential functions and logarithmic functions. I can almost hear your brain grinding and saying, but wait, aren't polynomials, they've got exponents in them, right? The difference between a polynomial function and exponential function, in a polynomial function, the variable is the base, and you're raising that to integral, in fact, positive integral, whole number exponents, okay? In an exponential function, you've got something else as your base, and your variable is your exponent. So that's the difference, okay? We'll go over that in a minute, okay? So 3.1 is talking about exponential functions and their graphs. You'll need to recognize and evaluate exponential functions with a base A. As I said, with a polynomial function, the base is your variable. The exponent is a whole number. In a exponential function, the base is some number A, and the exponent is your variable. Okay, the variable is your exponent. We'll graph exponential functions and use the one-to-one property, which we'll talk about what that is. We'll recognize, evaluate, and graph exponential functions with a base of E. Anyone know what E is? It is the base of our number system. We think we're a base 10 system. In reality, especially when you get into calculus and stuff, the natural base of our number system is the number E. The problem with it, it's an irrational number. A lot like pi is, but it's not the same as pi, like the square root of 2, square root of 3. Those are all irrational numbers. E is an irrational number, and yet it forms the basis of our number system. We'll use exponential functions to model and solve some real-life problems. So we'll probably try to get through these as quickly as possible. Exponential functions. So far, this text has dealt mainly with algebraic functions, which include polynomial functions, rational functions, those kinds of functions. Okay? In this chapter, you'll study 2 types of non-algebraic functions, exponential functions and logarithmic functions. And they are related, by the way. These functions are examples of what we call transcendental functions. Now, I think several of you may be signed up for trig or planning to. We'll do more transcendental functions there. Your trig functions are also transcendental, okay? Not algebraic. Actually, we usually call them trigonometric functions, but they are in a sense sort of like transcendental. Okay, the definition of exponential function, f with a base a, that can be anything. It could be 2, computer scientists use that a lot. 10, we use that a lot. 17 thirds, I mean, it could be any number. E, a irrational number, square root of 3, that's fine. Any base a, and then your function, exponential function, will be f of x is equal to a to the x. That base, that number, whatever it happens to be, raised to the x power. Your variable is your exponent. Now here's the requirement. I said it could be anything, not quite. A has to be positive. We don't deal with these when A is negative. The base has to be positive, but not just positive. Okay, it can't be 0, by the way, either. Positive, not negative, but positive. But it also can't be 1.
Why would they just put A greater than 1?
What's that?
Why can't they just put A greater than 1?
Because you see, you could have A as 0.5, 0.1, 0.72. Height, no, never mind. Okay, no.
But it can't be 1.
it can't be 1. Okay. It could be 0.5, it could be 0.9, it could be 0.999999, it could be 1.00001, it just can't be 1. And here's why. If A were 1, whatever you raise it to, the value is going to be 1. That's a pretty dull, uninteresting function. Okay? It's y is equal to 1. Okay? We can do that back in algebraic functions. Same thing with 0. If A was 0, it's always 0. Always. Okay? But if A is negative, you got problems. Because you know you can't take, if your x was 1/2 and A was negative, it's not defined. Okay? So that's why we don't have any bases being negative. They can be any positive numbers except 1. Okay. The base A is equal to 1 is excluded because it yields f of x equal 1 to the x, which is 1. That's a constant function, not an exponential function. Okay. You've evaluated a to the x for integer and rational values of x. Okay. Whether you realize it or not, you've done that. For integral values, that would be a cubed or whatever. That's no sweat there. Even rational values. 4 to the 1/2. What does that mean? The square root of 4. Square root of 4. The denominator is the index of your radical. The numerator is your exponent. Okay? 4 cubed is 4 times 4 times 4. That's 64. So you've done those before. Okay? However, to evaluate 4 to the x for any real number x, you need to interpret forms with irrational exponents. That's a lot tougher. Okay? A lot tougher. Okay. For the purposes of this text, it is sufficient to think of a to the radical 2. Okay? A raised to the radical 2 power. You can think of that, and radical 2 is an irrational number, root 2, square root of 2. The first so many digits are 1.41421356, and they just keep on trucking, never developing any pattern at all. Okay? That's what makes it irrational. So you can think of that as a number that has successively closer approximations of a to the 1.4. You can do that. I don't want to do it, but you could. A to the 1.41, a to the 1.412, 414, a to the 1.4142, a to the 1.414121, and you can keep on getting closer and closer, and you're going to get closer and closer to some value. That is what a to the root 2 is. Guess what? Your calculator will do it, so you don't even have to sweat it. I sure don't want to calculate these things. I would use my calculator. So guess what? You can just plug in a root 2. It's going to do the very same thing you're doing here, getting closer and closer to it, and then when it gets within its margin of error, it's going to stop. Okay? That's exactly what your calculator is doing anyway. So, it wants you to use a calculator to develop each function at the indicated value of x. Okay? You got a calculator? Hopefully it's at least a scientific calculator. Graphic calculators are fine. Phones sometimes won't do this, folks. Okay? Calculators are pretty close to necessary here. Okay? 2 to the negative 3.1. Do you know the key to use for that? I'll tell you on most calculators. Some calculators may be a little different. What you press is, let me get my pen back. Okay. Did you do 2 caret negative 3.1? Okay. That's the key that says exponent. Okay. What did you say the answer was? 0.11 what?
66291239.
Okay, something like that anyway. Okay? Now, time out. Is that a reasonable answer? Well, obviously, you're raising, okay, you could think of this as 1 over 2 to the 3.1. Well, 2 to the 3 is 8. So this is something close to 1 over 8. 1 over 8 is 1.25. I mean, 0.125. So yeah, this is fairly close to it, so that looks like a reasonable answer. Okay, how about this one? Alpha of x is equal to 2 to the negative x, but x is equal to pi. Well, again, you would be 2 caret negative, and then most calculators have a pi key. Okay? Now, let's think through and see what kind of answer we expect this to be. This is, again, going to be something 1 over 2 to the 3. So that's not going to be far off from what that is. I'm guessing very close. What do you get? Blah, blah, blah. Okay. 7 what?
323.
Okay. Good. So it's not far off from what the other one was. And guess what? You just evaluated an exponential function at an irrational base. I mean, not base, irrational value. Okay. Now, how about this one? F of x is equal to 0.6. There's a base less than 1 raised to the x. Well, that's again going to be 0.6. Actually, 0.6 will do. Caret. You can either write 3 halves. If you do 3 halves, be sure you put it in parentheses. 3 over 2. I would be tempted to do 0.6 caret 1.5. Either one of those is going to give you the same thing. Now, what kind of number do you expect this to be? A large number, small number, bigger than 0.6, less than 0.6? What do you think? Bigger than 0.6. Second?
Bigger than 0.6.
Okay, you would think so. But if you think about it, do 0.6 squared. What would that be? Yeah, it's going to be less. It's 0.36. So this is also going to be less. And it's going to be between 0.6 and 0.36. So I'm going to guess it's going to be something about 0.4, 0.5 something. 0.4 something probably. What did you get? Say again?
My batteries on my calculator just died.
Is it rechargeable? No.
0.6.
Say again?
Is it 0.6 or just 0.6?
0.7? Is that what you said?
He was asking what it is. I know it starts off as 4 point.
Oh, no.
I mean point 0.4. Excuse me.
0.4.
0.464.
Yeah, that sounds good. 0.464, blah, blah, blah. Because it has to be between 0.6 and 0.36. Okay? So 0.4 sounds reasonable. Did you plug it in like that? 0.6?
Which one am I doing?
Either one. I mean, it's 0.6 raised to the 3 halves. If you use the 3 halves, you have to do this. Why? Because the rule of order of operation. If you didn't have those parentheses, that's going to be 0.6 raised to the 3rd power and divide that answer by 2. That's not what you want. You want it raised to the 3 halves power. So just to save from making mistakes, I would go and do that 0.6 raised to the 1 1/2, 1.5.
Yeah, I got 0.46475
75 what?
80015.
0015. Okay, those sound reasonable to me. Let's see what the book got. First one, they got 0.11666291. That sounds pretty reasonable. They showed you how to do that. Okay. Now, if you have one of those older calculators, older scientific calculators, rather than this key, you may have x to the y or y to the x or a to the b or b to the a, one of those keys rather than the caret key. And with those older scientific calculators as well, you may not have the negative sign in parentheses. If you don't have that, you'll probably have a plus minus key. That changes the sign. And the really old calculator is CHS key, change sign key. In those calculators, either plus, minus, or change sign, usually you have to enter the 3.1 first and then hit the change sign key and then press enter, okay? So you have to know the syntax for your calculator. And guess what? You know, there'll be some of these on the test, maybe not problems like this. You need to have a calculator that'll do exponentials, okay? Try to have that. So yeah, we got something like that. Y'all had more digits than they did. This one's not far from it, 0.1133. Yeah, I remember you had that. And this one, and like I said, you have to put that 3 divided by 2 in parentheses. If you don't, you're going to get a wrong answer. 0.464. Yeah.
I just put the 3 over the 2.
What's that?
I just put the 3 over the 2. I did like 6 raised to alpha y equals and puts the 3 over the 2.
Okay, a fractional key. Yeah, then that's perfectly fine. Because a fractional key basically is put it in parentheses for you. Okay, good deal. All right. That was example 1. How are we doing on time? 7 minutes? Okay. We'll move on to graphs of exponential functions. On the same coordinate plane, sketch the graph of these two functions. Okay? I'm cheating big time because I know where these graphs are going. Okay? Let's tick off 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7. Okay? Now, when you go to graph a function, typically what do you do? How do you proceed to graph a function? Okay, sort of like a t-table, if y'all ever called it that. Okay, so let's do x, alpha of x. And then we're also going to do g of x. So this is going to be a triple t-table or something like that. Okay, so give me an x. 1, okay, I like that. What is 2 to the 1? 2. What's 4 to the 1? 4. Oh boy, y'all are good at this, aren't you? Give me another x. 0, okay. What's 2 to the 0? 1. What's 4 to the 0? 1. Very good, okay. Give me another x. 2. What's 2 squared? 4. What's 4 squared? 16, all right. Give me another x. Negative 1. What's 2 to the minus 1? 1/2. Excellent. What's 4 to the minus 1? 1/4. Exactly. Okay. Give me another x. 3. What's 2 cubed? 2 cubed? 8. Okay. 4 cubed? 64. Okay. Let's do one more, like negative 2. One-fourth. And 4 to the negative 2. 1 over it. 16. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. We're not going to get all those on here, obviously. Now, I'll do alpha of x in black. So let's do those first. When x is 1, alpha of x is 2. When x is 0, alpha of x is 1. When x is 2, alpha of x is 4. 1, 2, 3, 4. Okay. When x is negative 1, alpha of x is 1/2. When x is 3, Alpha of x is 8. 1, 2, 3, 4, 5, 6, 7, 8. Somewhere about there. Okay? When x is negative 2, this is 1/4. Okay? You see what's happening here? You have a horizontal asymptote to the left, 0. But you don't have, this just keeps growing and growing and growing. So like the Energizer Bunny, okay? Keeps going, it doesn't approach an asymptote, it doesn't approach anything, it just keeps growing. If we had done 4 here, it would have been 16, that's 1, 2, 3, 4, 5, 6, yeah, it would be off scale. Okay. Now, what color you want to do the g of x? Say again? I can't hear. I can't hear. Red. Okay. My hearing is so bad. Sorry. Okay. So let's do that one. When x is 1, y is 4. When x is 0, y is 1. When x is 2, y is 16. Already off scale before you get to 16. Okay? When x is negative 1, you're down here at 1/4. When your x is 3, you're way off scale. X minus 2, you're down at 1/16. Okay. Well, I can't get it to draw. Okay. Quit that. Okay. Somewhere down there. All right, what's going on here? Well, guess what? They both go through 0, 1. Hint, every exponential function goes through 0, 1, okay, if it doesn't have anything else on it. And here it's going up much faster, and here it's approaching 0 even faster. So that's basically kind of what they look like, okay? Let me clear this off out of the way. Any question on that? Okay, and see what they, oh, I didn't need to clear it. They picked a few points, okay, and there they have it. Would have been nicer if they'd have done it in color, like we did. But you see the 2 goes up, they both pass through 0, 1, and this goes up, and it gets big really quickly. But 4 goes big even faster. Now, we're not there yet, but we're going to. E, by the way, is the irrational number 2.7, blah, 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 blah. So it's going to be in between, but closer to the 2. It's going to go up a little bit faster than 2, but it's still going to go through 0, 1, 0, 1. Okay? Does that run us out of time? All right, let's see if they're. Note that both graphs are increasing. Moreover, both graphs are positive. G of x increases more rapidly than the graph of alpha of x. At least to the right for positive values. Yeah, I wouldn't say that about the negative. All right, we'll pick up next time. Where? Can't see where that graphic's coming from. All right, we'll pick up next time with example 3. They don't have example 3 on the slide set. So we'll do that next time. Let's see if there's any homework exercises there. I wouldn't sweat them even if there are. You might want to do some of the odds 7 through 11 and stop there. Just we did some like that in class. Good deal. Okay, sorry only 4 people were here, but hopefully others will listen over the weekend and find out we do have the test on chapter 2 on Tuesday. Be ready. Bring your formula and equation sheets. All right. Good deal.